Glassman. I'm the Global Training Manager for Fluke Corporation. A little bit about me. I've been at Fluke with Fluke for almost 30 years now and can answer the host of different questions that may arise during the presentation or other questions that you may have that are related to this presentation. So please type them into the chat panel or bring them up at the end of the presentation. Today's presentation will take a look at NFPA 70E, something called IEC 61010 from the International Electrotechnical Commission, which governs how we build actual products, and some of the things that you really need to understand when selecting a product and utilizing a product. And the presentation today will take approximately 20 minutes. We'll have a little bit of time afterwards, about 10 minutes, for any type of open discussion that may come up. So, electrocution. That's the obvious issue that brings us all here. It's a big issue in the industry. Anytime you're working around active panels is the understanding of live voltages and the possibility of having any type of arc flash or arc blast incident. And hopefully no one's experienced that. It's a very tragic event if anyone has. That's what we're here to try to avoid. There are some industry estimates I'd like to go over. Now these estimates are according with a company called Capshell Incorporated. They're in Chicago, and these incidents took place over a period of time, probably about a 7-year period, where actually 2,576 U.S. workers died and over 32,000 suffered injuries from electrical shock and burn injuries. And 77% recorded electrical injuries were due to arc flash incidents. And according to the estimate, 5 to 10 arc flash incidents occur every day in the United States. You know, we're using more energy now than ever before. Now there are a lot of advancements. For instance, lighting, which is now LED and controlled over a lower voltage, that's a good thing. But we still are subject to old infrastructures, going down into vaults with aging infrastructures and equipment, and the chance of having an arc flash or arc blast are actually increased. In this slide, you can see that there's a variety of different current levels that are applied depending upon the type of shock that you can get. Some, you're just going to feel a slight tingling sensation at about 1 milliamp with the current. As the current goes up, you're going to go all the way through from the slight shock that you feel to a painful shock where you actually freeze up, and that's called the let-go range. And that is, in fact, at between 6 to 16 milliamps, which isn't a lot of current. But that actually locks up your muscles from being able to let go of that probe or that screwdriver or that panel or whatever you're contacting in the way of the active voltage. Then you'll feel extreme pain. There's respiratory arrest, muscular contractions, then finally getting to, unfortunately, ventricular fibrillation, which uncoordinated pumping of the heart, and then cardiac arrest can occur. You know, it doesn't take much current as described here, and the average current of even a small little nightlight exceeds these limits. And obviously, we've all been told, don't stand in the bathtub and touch an electrical outlet, and that's because you're lowering your body's resistance. The epidermal is the outer layer of the skin, actually has high resistance. So any open wounds or any injury that can be a path for that electrical current is actually extremely dangerous. There are some risks from an arc flash. Now, the arc flash is created from a phase-to-phase or a phase-to-ground short circuit. Current passes through the air, and it's very similar to, I like to equate it to almost what we call a Jacob's ladder effect. And that's the old Frankenstein movies where you've seen the arc of voltage jump between two different V-shaped probes as it rises. Ionized air starts to heat, the arc travels upward until its resistance gets so high that it extinguishes itself, starts again at the bottom. And that's really what happens in an arc flash incident. So as you pull away from the contact point, that arc continues to grow, and if the arc crosses itself at any point, that's where you get the danger to occur, because that becomes that phase-to-phase connection. So there's a lot of danger in making the connection, and if an arc starts, obviously jumping across the two different phase connections. After the arc flash occurs, which is that bright light, unfortunately becomes that arc blast, and this is where the real danger does exist. And this is the explosive result of an arcing fault. This is where metal is vaporized, and at 740 miles per hour, it's forced away from the surface of the panel, and all of this liquefied metal is pushed towards you. If you're not wearing the appropriate PPE for the environment, unfortunately, that's where a lot of dangers do come from. As well as blinding light, the noise is horrendous. A lot of people have experienced ruptured eardrums, and all of this happens in the blink of an eye, actually faster than a blink of an eye. What likely causes them? First of all, racking a circuit breaker, especially if it's on a live bus. So if you're not working on a de-energized panel and you're doing a live testing, which you need certain authority to do within your organization, but racking that circuit breaker could cause something. Dust, any type of metal debris, filings from any of the stranded conductors. Anything can happen, especially when you're disrupting it. Loose panel wiring, where it breaks loose and actually comes down and shorts across another conductor. And we mentioned aging infrastructure. Obviously, a lot of the vaults that we work in, a lot of the panels, they're getting older. The infrastructure in the United States is starting to get older. And when we're asked to go in and make some measurements, it's like standing before a loaded cannon. Very, very dangerous. So removing the panel covers, when you take the screws out, it could disrupt something. A hand tool that's put on the top of the panel, and I've seen this happen where they take the cover off and the hand tool actually drops into the panel. Using incorrect test probes. When we looked at that drawing before, anything that's 3/4 of an inch or longer on the end of the test probe could be a source of a metallic content or contact for an arc flash. You need to minimize that amount of metal. And also misuse of measurement tools, and we'll cover that in a little bit, of what can happen when measuring in an incorrect mode, causing a short circuit to occur. Here are some common errors with measurement tools. First of all, you need to be aware of the test equipment that you're using. Many cases, someone may borrow a piece of test equipment because theirs is either in the shop, they forgot it somewhere, and they borrow a buddy's. The problem with that is you don't know the condition of the case of the fusing. If you're making a current measurement, which is in fact in series with a conductor or the loads, that could give you a direct short. And some people don't put in the right type of fuse. And it doesn't blow fast enough to extinguish any type of arcing situation, and that can be very dangerous. So amps mode on the meter is almost a short circuit. Also, measuring ohms or continuity on a live circuit, a lot of older meters can't do that. Now, Fluke meters are designed with a protection circuit that's built into the instrument to extinguish any type of arc where you can measure up to 1,000 volts in any switch position and nothing bad will happen. Not all meters are built that way, but I can speak to Fluke. Older meters, even though you may have an older meter, and we'll talk a little bit about this, may not be designed for the amount of currents that we're measuring today with the higher amperage circuits. You need to follow industry guidelines. Now, NFPA, National Fire Protection Association 70E, is the actual standard that you do need to follow, and you should be very aware of this. This works alongside and parallel to OSHA, but this deals with electrical measurement safety. And not just electrical measurement safety, but how we work in a safe way in an electrically charged environment. Now, this standard is renewed every couple years. With this presentation is dealing with the 2015 standard. There's a new one that we're just addressing now. But understand that you should always be aware of your company's industry guidelines when working under these active conditions. Always wear the appropriate PPE and use lockout tagout. And what does that mean? Well, the appropriate PPE can vary depending upon the electrical environment that you find yourself in. In some cases, at a minimum, it should be the protective gloves, eyewear, hearing protection, the leather shoes, perhaps other types of safety gear, all the way up to wearing a balaclava with the face shield, flame-resistant clothing at different therms, at different levels, and also following the correct procedures. So many companies deal with a lockout-tagout procedure where you're safing that panel, but you do have to be aware of any dual feeds that can possibly happen. So just be aware of that. Here are some safe working distances, or what we call flash limits of approach. And you can see that you do have the exposed conductor, and then there are some different areas. Now, these, I think, have changed in some of the more recent standards of NFPA, but the boundaries are about the same. The arc flash boundary is established at the outer perimeter depending upon the total current and voltage that's flowing through the system and the total ampacity of the whole system. And that's going to be an area where someone that is not wearing protected clothing cannot pass. So you have to wear appropriate, or wear the appropriate clothing, but also have the boundary put in place. When you get into the limited approach boundary, somebody that is trained needs to be able to, or can go into that space and into the limited space all the way up to the restricted boundary, where it takes a little bit more education and knowledge for somebody to be able to cross. There's an article, 110.4 in NFPA, that talks about PPE, that test instruments are in fact part of PPE. Part of these are, these are prints out of NFPA, but they shall be rated for the circuits and equipment to where they will be connected. And what's important there is make sure that the rating of the test leads matches the rating of the environment wherever you're making the measurement. And it's not just the test leads, it's test probes, it's anything connected to the meter and the meter itself. Shall be designed for the environment which they'll be exposed and used in the manner in which they'll be used. Visually inspected. So make sure you take a look at the meter, look for any oil leaks, any type of fading digits on the display, anything that could be subject to question, and you also need to validate its operation prior to using it on any exposed conductors. That is called an operational readiness test. We call it a live, dead live test. Now, just because you've performed a lockout tagout and you feel that you're safe, you still need to wear PPE when you go to that questionable panel that's appropriate for the panel. So you need to suit up. You can open the panel at that time, but you need to verify that, in fact, there is no active voltage on any of the conductors going into that panel. Some could be rewired, Someone may not have mentioned that there's a dual feed in the panel. It may be getting a feed from another circuit or another object. And in the operational readiness test, that's where we use what's called a proofing unit, and that actually generates a certain amount of voltage that's suitable for the environment. It's a known voltage. So you could use a convenient outlet, but if you use lockout-tagout, chances are that outlet is no longer powered. So this is called the PRV240. It's a small proving unit that generates 240 volts, AC or DC. So if you're working on a backup power supply on batteries, you can use the DC section. But you verify the operation of the instrument, and then you measure the unknown, and then you re-verify. So let me show you what that looks like. So here we have the live, dead live testing that's being done. Again, wearing the appropriate PPE, you measure a voltage similar to the voltage or equipment that it's about to be tested. And 240 volts is sufficient in most of the panels that we're measuring. So you verify the operation of the instrument. Then once you've done that, touch the unknown circuit and make sure that the instrument is reading 0. Then you re-verify the operation of the instrument on the known voltage source. And that's the only way and the only time that you should be able to take off any PPE is once you fully checked to make sure that it's deactivated. Now there's also some best practices for placing safety first. Whenever possible, obviously, work on de-energized circuits and follow proper lockout-tagout procedures. Use well-maintained tools, so check all of your tools. Don't work alone, and have a plan. Let people know where you are, and practice those safe measurement techniques at all times, and use the live, dead live testing. The danger comes from transients. A transient happens when a motor or an inductive load is switched off, or load switching from the utilities, or a lightning strike. And that's where up to 8,000 volts or so could ride on top of the sine wave and find its way to you through the instrument that you're measuring. What's important is to look at category ratings. So let's take a look. You need to make sure that your meter is set for the environment that you're working in. That is called International Electrotechnical Commission, IEC, big word. IEC 61010 is the standard, and all manufacturers of test equipment build their equipment with this in mind. There's something called creepage and clearance that is built into the instrument, where if it receives this high-level voltage, any type of arcing that takes place would either be extinguished or, in fact, held captive inside the instrument and not come through to the user, which is very important. So here we have measurement categories, locations, or ratings, category 2, 3, and 4. In this one, you can see that the greatest danger from transients is where we're measuring at the service entrance or at the SE to the building, and that's on the secondary side of the transformer. Again, our instruments measure up to 1,000 volts, which by utility standards are considered to be low voltage, still a lot of voltage. At the utility entrance, at the service entrance, that is where you're going to find the greatest amount of current that could cause this arc flashing incident. As you work your way into the building, for instance, category 3, that's for three-phase distribution and single-phase lighting systems. That is an environment that by the time it makes it to category 3, some of that energy has already dissipated in other components. Then once you travel further into the building structure and you come to single-phase plug-in loads, that's considered to be a category 2 environment. So you always want to check what category your equipment is designed to work in. And you need to select the proper category. Some of these can be dual categories, for instance, a category 3 and a category 4. And there's also voltages that are related with those, typically 1,600 volts. They also have 300 from time to time. In other words, if you're working outdoors, the highest rating is really a Category 4 600 volts. So you could feel safer by using that instrument if it's rated to Category 4 600 on any circuit that's connected to the mains. Always look for the cat markings between the input jacks of any instrument. It could be on a scope meter, it could be on any device. And here you'll see where we have Category 3 600 volts. There are some that are dual rated, the Category 3 1000 volts or Category 4 600 volts. What if you can't find the rating? Don't use the instrument. The bottom line is before 1997, we didn't have that rating structure in place, but now we're using circuits, we're using equipment on circuits that have a greater amount of current available. There's also independent testing and certification that goes through each piece of instrument. So take the instrument out of its protective holster, flip it over, take a look for CSA, TUV, UL listings, and that guarantees that in fact they still work well. Excuse me. Protections designed in. So with instruments, they use high voltage, high energy fuses that are actually sand filled to extinguish an arc. We have other overload protection and other capabilities that keep the instrument safe. About 10 to 15% of the cost of going into the meter is devoted to these safety features. Here's the fuses. A bit of recommendation, if you need to replace the fuse, whether it's a Fluke instrument or any instrument, always refer back to the manufacturer's recommendations on what fuse to use. Don't violate that. Very important that you use the correct fuse. As I mentioned, these are designed specially by Fluke, for Fluke, to have some sand inside, and it actually turns to glass, which extinguishes and smothers that arc that can be generated in the fuse if excessive current goes through. Perform an inspection of the test leads. Some of the test leads are actually shot with multiple layers of coatings. So there's a white coating under the black or under the red coating on the outside. Take a look through, make sure they're not cut, they're not damaged in any way. Take a look at the flexible restraints, the double insulation, the finger guards. Make sure that the test leads are in good working order. Test leads are an inexpensive part to any meter compared to your safety. I recommend replacing them at least once a year. Minimized exposed metal for safety. We talked a little bit about this. In the Category 4 environment, you can only have 4 millimeters. That's 0.16 inches of exposed metal. In a Category 2 environment, which is for the receptacle, that can be up to that 3/4 of an inch. Now, we have some special test probes. That's the TL175s that you can see in the picture. That actually rotates a guard that comes into place that's built into the test leads. Or you can use just some simple test lead probe insulators that you'll see on the left, and that you should definitely use in a Category 4 environment. Non-contact voltage detectors. You know, we've all seen these, we all use them, we all depend on them. And there's a place to definitely use them. The question becomes when to use a digital multimeter or contact type instrument rather than these probes. These work well to measure for the absence of voltage, but not the presence of voltage. Use only the digital multimeter or contact type voltage tester to test for that absence of voltage, not the presence of voltage. A lot of these we use if we're looking at a circuit to just see if it's hot or not. But if there's something wrong with it or you're not getting a very clear indication of active voltage, I still wouldn't trust myself to touch that contact. There's voltage and current measurements without metallic content. Now, we've just recently introduced something brand new to the market. It's called the T6, which doesn't take an active measure, it doesn't make an active contact with a conductor, but it still gives you the ability to measure both current and voltage on the display. So that's something that you may look into. It's something that can keep you away, again, from that active conductor whenever possible. You may consider providing physical separation for an arc flash environment. Anytime you can get out of that face of that cannon explosion that could possibly take place, you're better off doing it. So we have wireless tools, a variety of different ones, or some way to get a measurement outside the arc flash zone, away from a hot environment or a dangerous environment. So always use those. And stay well away from that energized equipment, well outside the arc flash boundaries. We also have some wireless tools where, in other words, they make the measurements. You can see in this panel, they're making measurements of three-phase current using some Rogowski coils on the current. They're also making some voltage measurements, and they're transferring over low-power Bluetooth all of those readings back to a cell phone that has an app, so you can measure these from a distance, or even send them up to the cloud for measurement. Also, infrared cameras. Infrared cameras, extremely important. They're really your front-end tool to go ahead and scan a surface and try to find out what is going on. There's a couple ways to use these. One is qualitative, another is quantitative. Most of the time, all you do is scan the surface to look at a qualitative measurement. In other words, focus on the area that is hot. That'll indicate excessive current, a loose connection, or some other issue that you really need to pay attention to. Here's some pictures from analyzing the invisible really with infrared. You can see the active conductors starting at the left drawing of some breakers or some fuses. You can see which ones look cool, in which case you may assume that that one might be even an open fuse. You might see some circuits that appear brighter and lighter in color. That can indicate excessive current on that circuit, perhaps even a lighting circuit. Finally, until we get to the right one, which shows some pole-mounted transformers, you can actually look at the oil levels inside a pole-mounted transformer from a distance and indicate some potential problems. Switchgear. I think IR windows, essential. If you have some switchgear, rather than opening the switchgear to make some specific measurements, if you're using thermal, definitely take a look at IR windows. Now, these are not glass. They're a special crystalline element that allows the transfer of thermal heat or thermal radiation through them, so they can be detected by the thermal imager. But once they're installed, and they only take a few minutes to install, then you can go in, open them up, take a quick scan of the panel to see if there are any problems, close them up again, and you're not exposed to the active power. Bottom line, read and understand all of the manufacturer's instructions on the instrument that you're going to use. That's essential. Next steps for you. We only have a couple more slides. One of them, we have some training that's available online. We have electrical measurement safety training. We have some DMM training, motor drive training, insulation tester training. Go to fluke.com, and under the training tab at the top, go to online training. We don't charge for it. Phenomenal training that'll bring you up to speed on using the instruments correctly and being safe when you're making those measurements. Also, make sure that you match your environment to your CAT rating of any tool that you're using. So do your own scorecard, you might say. Go through understanding where you're using these, rate them appropriately, take a good look at your instruments, replace the batteries at least once a year. Some people get them calibrated. You can think about that depending upon the criticality of your work and the accuracy that you need. But make sure you take a good look at the instruments and take good care of them. And finally, I want to thank you for the presentation and the time that you've spent with us today.